go. So that would mean that if we had magnesium, magnesium would fall up here in the all other category because it is not silver, it's not lead, it's not copper 1, it's not any kind of mercury, it's magnesium. And it would be soluble. So if I were to take magnesium chloride and dump it into the water and stir it around, what would happen? It would dissolve and ionize and break apart, right? And so you would have MgCl2, and what would the state be for that? Aqueous. So basically, anytime you see the word soluble, that means your compound will be aqueous. Anytime you see low solubility, that means the compound, if you put it in water, it will be solid. Okay. Now there's a few things that are worthwhile noting. Alkali ions. What group are the alkali metals? They're group 1. The alkali ions are soluble with what? That's a positive ion. Okay, those are our positive ions. They are soluble with everything. Okay, so if I give you sodium Na3PO4, is that going to put it in water, solid or aqueous? Aqueous. If I give you potassium hydroxide and you put it in water, is that solid or aqueous? Aqueous. I could go on and on and on and give you all the different examples and they would all be aqueous, okay? Same thing with the hydrogen ion. This one's a little weird because these are actually acids, okay? So they behave a little bit differently. Okay, and you'll also notice that who else is soluble with everything? There's another cation that is soluble with everything. Tell your partner, what is that cation? What other cation is soluble with everything? Ammonium, yes? NH4 plus is soluble with everything. And why do we know that? Because it says it is soluble with all anions. There are 2 anions that are soluble when you put them with anything. Who are they? Acetate and nitrate. They aren't soluble, they're soluble with absolutely everything. So if I give you calcium nitrate, tin nitrate, lead nitrate, manganese nitrate, all of those would be soluble, and same with your acetates. Okay? Now, it starts to get more interesting when we get down into the chlorides. How many things are low solubility with chlorides? How many things are low solubility with chlorides? 5. 1, 2, 3, 4. 5 things are low solubility. One thing I want you to take close note of, Copper plus. Not copper 2 plus, just copper plus. So if I were to give you CuCl2, what's the charge of copper in that compound, CuCl2? It is 2 plus. Is that going to be solid in water or will it be aqueous in water? It will be aqueous. But if I give you CuCl, what's the charge of copper in that compound? 1 plus, and so in water it would be solid. So the coppers are different. Watch out for that. It traps people every time. You know how like when you're driving along the road and you're going a little bit too quickly and maybe there's like a speed trap, like the police is there or there with like the little speed gun and you might say, oh, watch out for the copper. So in this case, you want to watch out for the copper. Oh, okay, because it's only copper 1 that's low solubility, not copper 2. Sulfate. How many things are solid in water with sulfate? 5 things. Okay, 5 things are not soluble. Everything else is soluble. Okay, here's sulfate. Sulfate. What's that? You will get this chart. Okay? Yes, but you'll get it on any test, whatever. Like, who tested this? Oh, it's really easy. You just drop things together and you see if you get a precipitate or not. You see if you get like a solid forming. Yeah. Sulfide. In fact, that's a very, very common first-year university lab. You just put combinations together, right? And you would pair things up with, say, nitrates that are always soluble, and you would mix it with something else that's like a sodium something, and then you'll know what you get as your precipitate at the end. Okay. I have been very kind to you this year. Have I been kind on the blue sheet? Let's see. Oh, I have been kind. When you get to grade 12, these will no longer be listed for you. Okay, it will just say alkali ions and you won't have them listed out for you. Okay? I know they're on the periodic table, but what'll happen is I'll say, is rubidium sulfide soluble? And if this part was missing, people will look and they'll be like, oh, no rubidium. Oh, it must be solid, because they'll forget to think about the alkali ions. So this year I've been very kind to you and I've listed them out. Okay, so you'll see, oh, rubidium. Rubidium is solid, but next year those will be gone. Okay, it'll just say alkali ions. I don't even know why we bother mentioning francium, because quite frankly, francium is so radioactive it does not stick around long enough to form a precipitate. But anyway, what you'll notice is as we go further and further down the chart, things become less and less soluble. Things at the top of the chart are soluble with everything. Things at the very, very bottom of the chart, they're soluble with almost nothing. They're only soluble with the things that are soluble with everything. You remember the alkalis are soluble with everything. Ammonium is soluble with everything. Hydrogen is soluble with everything. So if it's not one of those, phosphate, carbonate, and sulfite will just all be solids. okay, with whatever they're put with, unless it's one of those always soluble things. Okay, so let's predict the state barium sulfate, BaSO4. Try that one without looking at the answer. BaSO4. So maybe you can use your blue sheet. What do you guys think? Will it dissolve or not dissolve? Solve or not dissolve? Everyone go. Not dissolve. Okay, because you look here and you say, I have sulfate. And then I've got barium. So first you look up the anion, then you look up the cation, because it's easiest to go to the anion first. So anion and then cation, and then you look at its solubility, low solubility, and therefore it's going to be BaSO4 solid. Let's try aluminum hydroxide, AlOH3. Soluble or not soluble? Not soluble. Once again, you look up your negative ion, there's your hydroxide. And if you look, aluminum is not up here. Not there. Aluminum 3+ is down here, so it's low solubility. All right, let's try copper 2 chloride, CuCl2. CuCl2. Soluble or low solubility? Soluble. If you had low solubility, you were thinking of copper 1. Okay. What about, let's see. So this is now on page 68. Page 68. It can be really helpful to memorize that all salts containing ammonium, the alkali ions, nitrate, and acetate are all soluble all the time. Now, do you have to memorize it? No, because you have the blue sheet, but sometimes it's really nice not to have to think about it. You can look and be like, copper nitrate. Oh, it's soluble because it's a nitrate. It makes predicting products of double replacement reactions and finding their state really fast if you know these ones. Okay? So memorize if you wish to. Don't have to memorize because it's on the sheet. Okay? I'm going to let you guys do those exercises later because we already did a whole bunch as practice. All right, double replacement, predicting products. We're not going to watch the video. Do you want to watch the video? Okay, I have to type this thing in then. Windows left, because I don't have a, okay. Okay. H5KESS3M. Let's hope that worked. Hooray! This video isn't available anymore. Well, I guess we're not watching that video. All right, so let's just define the term precipitate. Do you guys remember the term precipitate? It is when it rains. It's when the little water drop, like vapor, they collect together and they condense and they form a liquid. A similar process happens, and in fact, on the video, there's a little demonstration. I'm going to show you that demonstration now. Hey. All right, I have PB NO3 2. I have PbNO3 2. And I put it into water. What state should I put beside it? PbNO3 2, I put it into water, and it should be aqueous because nitrate is one of the things that is always soluble. So I'm going to take this little test tube here, and I'm going to put some lead nitrate in here. And you'll notice it looks just like water, okay? Lead nitrate is actually quite toxic, so you don't want to do that. I'm just going to put it in my little teacup full of paper clips, okay? Now, not my teacup that I drink out of, it's my teacup full of paper clips. Okay, plus I also have potassium iodide, Ki, and I put it in water, and is it solid or is it aqueous? It is aqueous because K is a alkali metal. So it is, all the alkali salts are soluble. And I'm going to put that into a separate test tube. Okay. There we go. And again, it looks a lot like water. Super exciting. Well, if you drink the lead one, you won't die immediately, but it will contribute to the overall level of lead in your blood and in your body, and it will stay in your body. It accumulates in your body. It does not leave your body. It accumulates over time, and lead is a carcinogen, so it will contribute to any possible cancers that you might have. So don't drink it. Simple and straightforward. All right, are we ready? If you blink, you're going to miss it, so let's watch carefully. Here we go. 5, 4, 3, 2. What the heck, right? Now, you'll notice that we cannot see through here, right? Can you see through here? No. What is causing the light to bounce back? All the little particles of what state of matter? Solid. This is a suspension where we have solid particles suspended. Do you remember that from unit number 1, like way back when? Okay, and in fact, we could take this. Do you want to, have we seen the centrifuge? Have you guys seen the centrifuge? No? Oh, we need to centrifuge. Here. Okay, centrifuge. Now, before I plug this in, I'm going to try to kind of tilt it towards you so you can see what's in there. Okay, do you see how it spins? Can you guys see over here? If you can't see, feel free to stand up, move closer. Okay? Now, these little doodads here are meant to hold the test tubes, and you'll notice that they're on an angle. Okay, so they point out like this. Now, does anyone have an old style washing machine, like a top loading washing machine? Anyone? Everyone else loads in the front? You have one? Okay. If you ever used a top loading washing machine, I still have one because we got it 20 years ago and it's still going fine. It spins around during the spin cycle to get all the water to go out. Okay? Now, if you have an unbalanced laundry load, like heaven forbid you should put a pillow in your washing machine, because then all the weight is on one side, and instead of spinning nicely, it goes, and it actually starts to move across the room, like it really will, and then it'll go bang, and then it'll stop because it's like, okay, I'm not happy with this. There's like a fail-safe measure that makes it stop at some point. Anyway, very exciting. Yes? That might be one of the reasons. I don't think it's the main reason. I think the main reason is when you have the top loading one, it's got like a little spiral sort of paddle on the center post, and it actually makes contact with the clothes, and that's how the clothes get mixed. And I think it's harder on clothes than just being tumbled around in this direction, right? Because you've actually got things like touching the clothes to make them move. So I think the front loading ones make your clothes last longer. But the nice thing about a top load, you forgot to put something in and it's just started filling, you can just throw more things in, right? Like you can stop it at any point, you can start it at any point. It doesn't have to drain, nothing like that, whatever. Anyway, so if I want to spin this, okay, what's going to happen to the solid? It's going to go down to the bottom because it is more dense. Yes? Some of it might also go to the outside because it's being spun, you know, that way. But what if I just put this in here like this? Remember my story about the washing machine and the unbalanced load. It might go and fall off the desk. So we need to make sure before we go that we have something to counterbalance it. And so we're going to take some water and fill the test tube up to approximately the same level. Okay, doesn't have to be exact. Okay, there we go, close enough. All right, so now we have it counterbalanced. and I put them right opposite one another. Okay, one on one side, one at the front, one at the back, or one on the left, one on the right. Now, this is the fun part. You close the lid. Okay, in order to open the lid, you have to press the two little buttons and then you open it up. You close the lid, you turn it on, and it starts to spin. And you can hear it humming. That's a nice hum. That's not a thunky, thunky hum. It's not moving. It's not shuddering. Now, I will let you know that if you ever use this, which you might do if you're in grade 12, at some point, you will need to turn it off, because if you need to spin it for 1 minute, the little timer here doesn't go for a minute. It won't even turn on. It assumes that if you set it for 1 minute, it's in the slowing down process. So it will just go really slow. So normally I turn it on to about 10 minutes. I wait for about a minute, and then I just turn it to 0 and turn it off. And this is the best part ever. You have to listen. Is that not the most satisfying little thing ever? It's like the toast pop. Anyway, hopefully what we shall see, and we'll wait for it to stop spinning. And once it gets slow enough that you can see everything, you can just gently slow it down, but you don't want to do that while it's spinning quickly. That was our blank. And you can see on this one, all the solid is on the side and the bottom, and all the liquid is on the top or the front. Now, we can then, actually I should use that one. So this is a centrifuge. And now we are going to pour off the liquid and leave the solid behind. That process is called decanting. So I'm going to decant. And look what I got here, right? Clear liquid. And here I have a yellow solid. So let's take a look at that reaction and figure out what is the yellow solid, and is there anything in here still other than water? Because before we had things that looked like water, but they weren't water, right? They were like lead nitrate solutions. So let's take a look at those. Okay. Okay, so when we go to write a double replacement reaction, we take our outside ions. The outside ions are the ones that are on the far side of each compound. So I'm going to take the lead, which is on the far left, and the iodide, which is on the far right. And I'm going to combine them together. Now, my question to you is the correct formula for lead with iodide PbI? Ooh, there's a 2 here. What does that tell you about lead? It is Pb what? 2 plus. Do you know the charge of iodide? Iodide is -1. So what's the correct formula? PBI 2. Okay? If you don't write the correct formula, will you be able to balance this reaction? No, it will not work. You'll be like, oh no, it doesn't work. All right, we did the outside ions. Guess what we'll do next? We'll do the inside ions. So the inside ions are the K and the NO3. First thing I want you to ask yourself, which is going to go first in the formula? Is it the NO3 or is it the K? It's going to be the K. So often when I do these outside insides, I draw the outside arrow going that way, and then I draw the inside arrow going this way. Yes, because that way I'm like, it's going to be K with NO3. Plus KNO3. Is that the correct formula for potassium nitrate? What's the charge of K? +1. What's the charge of NO3? -1. Is that the correct formula for potassium nitrate? Yes. If you memorized the ions that you know are always soluble, you would be able to tell me immediately that one of these two compounds is aqueous. See if you can tell your partner which of these two compounds in the products is aqueous. Which of those two compounds is aqueous? It's the KNO3 because potassium is an alkali. All alkali salts are soluble. It also has a nitrate, and all nitrate salts are soluble. So that means that from both sides, this thing is as soluble as it gets, right? So it's aqueous. And we did get a solid. So that means I don't even need to look it up. But I know that if I got a solid in that and the KNO3 is aqueous, then this had to be the one that formed the solid. Could you look on your table and check and see if that is correct? Is PBI2 indeed a solid? Is PBI2 a solid? Yes. Okay, so that's super duper, that's awesome. Let's balance this sucker. I think all we need to do is put a 2 here to give us 2 NO3s, and then a 2 here to give us 2 Ks and 2 Is, and we're good to go. The word precipitate. It is a solid that forms when two aqueous solutions are mixed. Who is the precipitate in this equation? Tell your partner, go talk with your partner about that. Write it down first, and then I'll repeat the question. So who out of our reactants in that equation, or sorry, not our reactants, all of the substances in that equation, who is the precipitate? Is it PbNO32? Is it Ki? PbNO32? Is it Ki? Is it PbI2? Or is it KNO3? It is the PbI2, yes indeed. This right here is our precipitate. How can you tell that a precipitate has formed? What would you observe? Tell your partner, what would you see that lets you know that a precipitate has formed when you mix two aqueous solutions? The liquid becomes not solid, but like what would you actually see? Because you can't see the little tiny solid particles. What does it look like? Yes. Is it clear? When we pour it together, it's not clear, right? So it is cloudy or opaque, okay? It becomes cloudy or opaque. It just depends on how much of the precipitate there is. If there's only a small amount, it will only look cloudy, okay? If there's a lot, like we had, it can look opaque, and that's because the solid particles scatter the light. I don't know that I want to watch this video here. So let's not. Oh no, the page is sideways. Ooh, how can I fix that? You guys are going to chill for a second while I reprint this thing. Or you could go back to, actually you could go back to 6.3e and do the questions on page 68. Okay? Hi. Yeah.